Hi, in this video we are going to implement a ray tracing program. It is in the homework framework as usual. The first structure in the program is the material that represents the parameters needed for various illumination models, such as for rough surfaces that are specified by the ambient reflectivity, the diffuse reflectivity, and the specular reflectivity, as well as the shininess. For reflective, optically smooth surfaces, the surface can be represented with the Fresnel function computed for the perpendicular illumination, and we denote it with F0. And when the surface is also transparent, therefore refractive, we will need the index of refraction in the calculation of the direction of the refracted ray. Note that this index of refraction is a float or scalar parameter because we do not want to simulate dispersion. So when the refraction direction is obtained, we assume that the red, green and blue components go into the same direction. We need to know which parameters are valid from this huge collection of material properties. Therefore, we store the type of the material, and the material can be rough, reflective, and transparent or refractive. To initialize these parameters, we derive specific structures or classes from the base type, and the constructors will be responsible for filling up these parameters. So a rough material fills up the ambient, diffuse and specular reflectivity and initialize the shininess parameter and sets the material type to rough. A reflective material is defined by the index of refraction and the extinction parameters, which can be different on the wavelengths of red, green and blue. Therefore, we use the VEX3 type for their identification. The material type is set to reflective, and we have to compute the Fresnel function for perpendicular illumination, for which we established this formula. Note that in this formula N1, kappa are all VEX3 types, they are all spectra, and the operator overloads determined how these spectra should be multiplied together, added together, or divided one spectra with the other. The rule is always that the same operation should be executed for the three components independently of other components. If we have a refractive transparent material, then kappa, the extinction coefficient, must be 0, because if kappa were not 0, then the object would not be transparent at all. So we implicitly assume that the extinction coefficient is 0, so the input parameters include only the index of refraction, and therefore we can use a simplified version of the formula for the Fresnel function for orthogonal illumination. Additionally, we store the index of refraction for the Snell's law. It can be either the average of the index of refractions on the three wavelengths, or here we use just the index of refraction valid for the red component. In ray tracing, the ray surface intersection should be computed. The result of this computation is this heat structure that includes the T, which is the ray parameter of the intersection, and as the ray is just a half line, we assume that this T parameter must be positive in order to represent a valid intersection. And when the ray doesn't intersect the object, we indicate this case with an invalid ray parameter, which can be, for example, -1. In addition to the ray parameter of the intersection, we also store the location of the intersection in vert coordinates. the surface normal at the intersection point and also the material properties at the intersection point. The ray is a half-line identified by its start and direction. Note that in the constructor we also normalize the direction vector, because in the illumination computation we usually assume that the involved vectors are unit vectors. So we already prepare for that. The base class of geometric objects is the intersectable, because in a ray tracing application the most important thing we want to do is to compute the intersection between the surface and the ray. So this intersection calculation is the intersect function. It's a pure virtual function here, therefore intersectable is an abstract class, because without knowing the equation of the surface we cannot really implement the intersection calculation. Well, in all cases intersectables have material properties associated with them. So when it comes to a particular object, for example, to the sphere, in this simple example, we have to derive the sphere from the general intersectable class, and as the sphere has already parameters describing the geometry of the sphere, we can give the intersect valid implementation. So for the sphere, the parameters are the center of the sphere and the radius, and based on these parameters we can determine the intersection point of the sphere and the given ray. It can happen that there is no intersection, which becomes known when we try to solve the second order equation established as inserting the ray equation into the implicit equation of the sphere, and this second order equation has a discriminant that is negative. So in this case there is no real root of that second order equation, which means from geometric point of view that the ray doesn't intersect the sphere. In this case we return with the heat structure, where in the constructor the ray parameter is initialized to a negative value, indicating that there is no intersection. Otherwise, the second order equation is solved, and we may have two different real roots. From these two roots we need that root that is positive, and if we have two positive roots, that root that has a smaller value. If this is available, this ray parameter is included into the ray equation, so we get a position in vert coordinates where this intersection occurred. Additionally, we need to compute the normal vector of the surface at the intersection point. For a sphere, this is very straightforward, because the difference between a point on the surface and the center of the sphere is always perpendicular to the surface, and we even know the length of this difference. This is equal to the radius of the sphere, so dividing with the radius of the sphere we can immediately normalize the result. However, I have to emphasize that this simple calculation is valid only for the sphere. Finally, we also store the material associated with this point or with this object and return with the calculated heat. The camera represents the user in this virtual world setting his eye position, that represents one of his eyes, and we also need to introduce a rectangle in the virtual world that represents the physical screen. This rectangle is specified by the center of the rectangle called the look-at point, the right vector of that rectangle that points from the center to the right edge, and the up vector of the rectangle that points from the center of the rectangle to the top edge. In the set function, these parameters are calculated, making sure that the right, up, and the difference between the look-at and the eye vectors are perpendicular to each other. Otherwise, we would get a distorted image. This get ray computes a ray corresponding to a physical pixel of pixel coordinates x and y. And to do that, first the physical pixel coordinates are converted to normalized device coordinates separately for x and y. These normalized device coordinates run in the -1, +1 interval, and with these normalized device coordinates we compute a combination of the right and up vector. Adding the lookat vector, the sum of these three vectors will be a point on the camera rectangle. Subtracting the eye position from this camera point, we get the direction of the primary ray. We also have a camera animation which rotates the eye around the lookat point. So we can have a look at the scene from different perspectives. The light structure is for light sources. In this simple example, we handle only directional light sources defined by the direction and the emission intensity. The emission intensity is a spectrum, so it has a different value on the wavelength of red, green and blue. Therefore, we also represent emission intensity as a vec3 type, although it has nothing to do with geometric vectors. The direction is normalized in the constructor because, as I said, during illumination computation, we usually assume that these vectors are unit vectors. The scene is a collection of objects. Generally speaking, it's a heterogeneous collection because we can derive different geometric types from the abstract base class. Additionally, we can have arbitrary number of light sources in the virtual world and a single camera, and LA is the ambient light that is available in all points and in all directions. Build builds up the virtual world, that is, it fills up the list of objects, light sources, initializes the camera and the ambient light source. So first, the camera is initialized, so we can specify the location of the eye, the preferred vertical direction and the lookat point, and the camera's set function computes the parameters needed in the camera, including the right and up directions. This is going to be the ambient light intensity on the wavelengths of red, green and blue, and we introduce a single directional light source with this direction vector and its LE emission intensity. This is the definition of geometric objects. We have only spheres, so all of them are spheres. For the constructor of the sphere, the first parameter is the center, and the second parameter is the radius, and the third parameter is the material properties associated with this sphere. So the first sphere is of rough material. We use the same specular reflectivities for all rough material surfaces, a little bit different shininess parameters and quite a different diffuse reflectivities. So the first sphere will be a kind of yellowish, the second a kind of cyan color, and the third one is sort of magenta color. In addition to these three rough surface spheres, we have a transparent refractive object. The index of refraction is 1.5 on all wavelengths, which corresponds to the physically valid gloss material. And the final object is a reflective material specified by the index of refraction on the three wavelengths and the extinction coefficients on the three wavelengths. And these parameters are copied from a physics textbook because these parameters are the real parameters of silver. So we will have a silver sphere in a virtual world. So calling the build function, the virtual world can be defined. Then we can render it. Rendering computes the result in this image array, visiting every physical pixel one by one, row by row, and then in a single row from left to right. And when we are at a particular pixel, we call the camera's getRay function to obtain a ray corresponding to the physical pixel in the virtual world, and with this ray, the trace function should calculate the radiance delivered by the ray That is, first it has to identify that surface which is first hit by this ray and then calculate the radiance reflected by that surface into the direction of the eye. The trace function returns with the calculated radiance that is written into the color variable, and finally it is written into the image array. So running this double loop, we can fill up the pixels in the image array. But this render function refers to the trace function that computes the reflected radiance of the surface first hit by a ray. The trace function is here. So it gets the ray and it also gets the recursion depths, which will be used to limit recursion and to avoid the crashing of the program because of stack overflow. So if the level of recursion is greater than 5, we terminate the process and return with the ambient light. Otherwise, the first intersect function will determine that surface which is first hit by the given ray and returns the hit structure. Recall that if the hit structure has a negative ray parameter, it says that that ray didn't intersect any object, so we see nothing, or in other words, we see the ambient light, because the ambient light is the same in all points and in all directions. If we really see some object, we first check its material type. If it's rough, the reflected radiance is initialized to the ambient reflection, then we visit abstract light sources one by one, and for every abstract light source we first determine whether this light source is visible from the shaded point or not, and if it's visible, its contribution is added to the reflected radiance. So first, for the visibility calculation of the light source, a shadow ray is established from the shaded point that is modified a little, and this shadow ray has the direction of the light source in case of directional light sources. We modify the start point of the ray a little, pushing the start point into the direction of the normal. The explanation of this modification is the following. If we start a ray from a surface, that ray will intersect that surface for sure with t equals 0 ray parameter. Recall that when t is not positive, we should ignore the intersection. So in theory, that works. However, in practice, due to numerical inaccuracies, it can happen that instead of the 0 ray parameter, we get a small positive value. So as a result, the surface will occlude itself. So to avoid that situation, we push the starting point a little away from the surface to avoid self-occlusion. The reflected radiance for rough surfaces includes the geometric term that is the cosine of the angle between the surface normal and the illumination direction. As these vectors are unit vectors, the dot product, the scalar product function determines the cosine of that angle. If this cosine angle is negative, or in other words, the angle is greater than 90 degrees, then the light source illuminates the back side of the surface, so the object occludes the light source from the shaded point. So if this cosine angle is not positive, we ignore calculations. If this is positive and the shadow calculation implemented in the shadow intersect function reports that there is no other object in between the shaded point and the light source, then the contribution of the light source is added, and first we use the Lambert's cosine law. So the contribution is the light source emission multiplied by the diffuse reflectivity. Both of them are spectra, so this product should be calculated independently on the wavelengths of red, green and blue, and finally scaled by the non-negative geometric term. The remaining three lines add the glossy reflection. For the glossy reflection, we need the halfway vector in between the view direction and the illumination direction. As these vectors are unit vectors, adding them up, we get a vector that is in between them, which needs to be normalized as well, because here in the next row, we compute the cosine angle between the normal vector and this halfway vector with the dot product. If this cosine delta is also non-negative, then the von Blin term is added, which is the emission intensity multiplied by the specular reflectivity multiplied by the shininess power of cosine delta, as proposed by von and Blin. If we consider all light sources, all light source contributions are added to the gradient, so we can return with this result. So the remaining part of this function handles optically smooth surfaces like ideal mirrors or refracting surfaces. In all cases, we need the Fresnel function. The Fresnel function needs the cosine of the angle between the view direction and the surface normal, so it is computed again with a dot product. We have an approximate formula for the Fresnel function that uses this cosine angle and also the Fresnel function for perpendicular illumination, which has already been computed. So if f Fresnel function is available, and we will know the amount of incident radiance from the ideal reflection direction, that incident radiance should be multiplied by the Fresnel function in order to get the reflected radiance. To get the incident radiance, first we calculate the reflection direction. Let's go back to the lecture slides for a moment, and let me remind you that we have already solved these problems and we established a formula for the reflection direction and also an implementation for the reflection direction. So this can be copied to the real implementation here, taking into account obviously that the variable names are different. So if we have the reflection direction, we can establish a reflection ray starting at the shaded point, pushed a little in order to avoid self-occlusions, and the direction of the reflection ray is the ideal reflection direction, meeting the requirements of the geometric law of reflection. And the trace function is called recursively, that trace function that is being implemented right now. When a recursive call happens, we increase the depth parameter because it will help us to control the depth of recursion and to avoid the stack overflow. If trace returns to this point, it will give the radiance delivered by the ray defined with the direction of the ideal reflection direction. So this reflected ray radiance should be weighted with the already computed Fresnel function. So we get in the auto radiance variable the reflected radiance due to ideal mirror-like reflection. If the surface is transparent or refractive, we need to add the contribution from the ideal refraction direction. Again, let's go back to the lecture slides, and I want to show you this derivation and the corresponding implementation, which determines the refraction direction using the incident direction and the surface normal, and using the index of refraction, which we assume here that it's just a float or real parameter. So we copy the formulae developed during the lecture here, making sure that the formula is valid for real numbers, because sometimes it can happen that there is no refraction direction, so these cases should be identified, and when this is the case, we shouldn't try refraction calculation. Otherwise, this is the copy of the refraction direction calculation formula, and we call the trace function again with the shaded point as the start, pushed a little with the calculated refraction direction, and when trace returns, it delivers the radiance from the refraction direction, which should be weighted with the 1 minus Fresnel term. and we are done for optically smooth surfaces as well. In the trace function implementation, we refer to two functions called the first intersect that determines the first intersection with the ray and the surfaces, and we also refer to the shadow intersect, which determines whether there is any object in between the shaded point and the light source. In fact, shadow intersect can also be implemented with first intersect. Shadow intersect is in fact a simplified version of the first intersect, because in case of shadow intersect we are not really interested in which object is in between the light source and the shaded point and which object is closest to the shaded point. In case of first intersect we also need that information as well. So for the implementation of the first intersect, we visit intersectables or objects one by one, try to check whether the ray intersects this particular object. Intersect function returns with the hit structure if there is an intersection, and this intersection is closer than the already found first intersection, then the current intersection will be the best choice for the first intersection. So at the end of this fourth cycle, we will have the hit information associated with the first intersection in the best hit structure. Note that in the formulae of reflection direction and refraction direction, we assume that the normal vector points towards the arriving ray. So it makes sense to make it sure that this always happens. This is done here. We check whether the ray direction and the normal vector point into the right direction, and if they are not pointing in the right direction, then the normal vector is flipped. Shadow intersect, as I said, is just a simplified version. We process all objects one by one, and if there is an intersection with one of the objects in this direction between the shaded point and the infinitely far directional light source, then we return true, indicating that this point is indeed in shadow with respect to the infinitely far directional light source. Practically, we are done as far as ray tracing is concerned. In the rendering function, this image is computed, which will be available in the CPU memory, and we can do whatever we want with this image. In the remaining part of this program, this image is displayed by the computer screen using the strategy which we already learned. We consider this image as a texture and draw a full screen or full viewport quadrilateral textured with this image. So it makes the image visible to the user. To do that, we need a vertex shader. This vertex shader assumes that in input register 0 we get vertex position in normalized device space. So C indicates that. It's worth giving vertices in normalized device space directly, because vertex shader should always transform points to normalized device space. So if it's already in normalized device space, you can save that transformation. So the GL position is just a copy of the input data with the extension to 3D and with the replacement of Cartesian coordinates by homogeneous coordinates. We will render a quad, a textured quad, so we will also need texture coordinates. Texture coordinates have a little bit different interpretation than normalized device coordinates. Namely, the lower left corner in normalized device coordinates is -1 and -1, and in texture coordinates it's 0 and 0. So the input normalized device space coordinates should be transformed from the -1, 1 interval to the 0, 1 interval to make it a texture coordinates. And this can be done by adding 1, 1 to the x and y coordinates and dividing the result by 2. The vertex shader output is the texture coordinates, which is interpolated, while the rasterization unit will identify pixels that are inside this quadrilateral. And for every pixel, the fragment shader is called. The fragment shader gets the interpolated version of the texture coordinates, and with this interpolated texture coordinate, the texture is looked up via a sampling unit called texture unit. This sampling unit is a uniform variable. So we get that texel color that corresponds to the particular pixel. So we will have a textured quad at the end. Well, on the CPU side, the textured quad is represented by this class. So for every geometry, we need a vertex array object, and it is a textured object, so we will also need a texture identification number. During initialization, we ask for a vertex array object identifier, bind it, and we also create a vertex buffer object storing the 4 vertices of the quad. These vertices are directly in normalized device space, so the xy coordinates are -1, -1 for the first corner, +1, -1 to the second, and so on. These vertex coordinates are copied to the vertex buffer object on the GPU, and we say that these coordinates will show up in the input register number 0 for the vertex shader. We have another resource, the texture itself, so ask for a texture identification in the texture ID variable. We also bind this texture because these functions will be expected to refer to that particular texture which have just been created. And initially we set the sampling parameters to bilinear interpolation, both for the case of minification and magnification. Load texture copies the image to the texture memory with the GL text image 2D function. During draw, we bind the vertex array object, the quad, and we set the uniform variable identifying the texture sampling unit. A GPU hardware has many texture sampling units from which we can select any available one. So here we select the first one that's identified with index number 0. This index number 0 is copied to the uniform variable in the fragment shader, and we also make it sure that this texture sampling unit is connected to that texture which we want to see on our rectangle. So one side of the texture sampling unit is connected to the fragment shader, and the other side of the same texture sampling unit should be connected to the image. To do that, we activate the selected texture sampling unit and bind the texture again, which establishes the connection between the texture image and the texture sampling unit. So if it is done, we send a quad containing 4 vertices down the rendering pipeline, and the quad is just a convex polygon, so the GL triangle fan is just an appropriate time for its rendering. In the initialization of our application, we set up the viewports, build the virtual world. So we initialize the objects, the camera, and the light sources. We create a full screen quad, asks for a vertex array object to represent the vertices, and also creates a texture, an empty texture at that moment. The vertex shader and the fragment shader are compiled and activated on the GPU, and that's the end of the initialization. So during on display, when something needs to be drawn, we call the scenes render function to compute the image with ray tracing, and then the computed image is used as a texture on the GPU, and a full screen quad is rendered that is textured with that image which was copied here to the GPU memory. And finally, we swap the 2 buffers to enable the user to see the result. The program doesn't react to user inputs, and when some time elapses, the scene is animated, which means that we rotate the virtual eye position a little around the lookout point and invalidate the screen, which means that we can expect a new on-display call. So with the modified camera parameters, the scene is rendered again. Let it run. So we have 3 rough surfaces and a transparent sphere and a big mirror-like reflecting sphere.